Hello, welcome to our continued journey into probability. Today we're going to look at problems that have the word or in them and problems that have the word and in them. You have faced these words before back in talking about the sets and Venn diagrams. We had or and problems there. Typically or was union, and was intersection. And also when we dealt with logic truth tables, we had or and there as well. You have or, union, that was your disjunctions, and intersection, that was your conjunctions. Well, now we're going to apply it to probability. And really the same deeper meaning exists, but we're not going to harp on that too much. But we are going to look at, well, what exactly is happening when you see those words and we're dealing with probability. Starting with or problems. You've already had some or problems in this probability unit, but let's look at them again. When you're presented with a compound probability problem with the word or, you need successful outcome for at least one of the events. We talked about this at length with logic, where if it's this or that, you need at least one of them to be true for the statement to be true. Well, in the case of probability, you need success for at least one of the events, this event or that event. Probability of A or B. Either A or B needs to be successful, but they both can be successful. Just it depends on the situation. But how you compute the probability is given there with that formula. If you have probability of A or B, it's probability of A plus probability of B minus probability of A and B. All right, so rather than throw that formula at you, let me give you some examples and then show you, well, this is how the formula works, and you can use the example to see it. Okay, for instance, let's say we're rolling a single die. And most of your or questions are typically going to be one event. So like here, roll a single die. So our little die, cubical die with 1 through 6 on it. So we're going to roll one of those, and we want to figure out the probability of rolling a 5 or a 6. Well, on your single die, there's 6 total outcomes. And for 5 or 6, those are your desirable outcomes. There's one way to get a 5, one way to get a 6. So there's 2 total desirable outcomes. Number of desirable outcomes. So you get 2 6, which is really reduces down to 1/3. So every 3 times you roll the die, one of those times it should come up a 5 or 6, according to probability. And of course that's theoretical, so it's also based on if you did this millions of times, roll that die, every 3 rolls would have one of those being a 5 or 6. Okay, let's say we have probability of rolling an odd number or a number greater than 4. Okay, again, there's 6 total possible outcomes when you roll that die one time, because there's 6 sides it can land on, and every side's equally likely to come up. And when you think about rolling the die, you have odd numbers. You can get a 1, a 3, or a 5. Those are your possible odd numbers because it has 1 through 6 on it. And then number greater than 4 would include 5 or 6. So 5 appears in there twice, but it's only one desirable outcome. We have 1, 2, 3, 4 distinct desirable outcomes. So that's the number of distinct desirable outcomes. Even though 5 shows up twice, we don't count it twice. Over 6 total possible outcomes. And then 4/6 reduces to 2/3. So every 3 times you roll the die, 2 of those times it should show up as an odd number or a number greater than 4. Okay, so those are examples of some OR questions. Now back to the formula. Our formula for probability of A or B is probability of A plus probability of B minus the probability of A and B. Okay, so how does that translate here? Because you may not always be able to come up with the numbers and count so easily, so you need to be able to use formulas if in certain situations. All right, probability of 5 or 6. That is the same thing as probability of 5 plus probability of 6 minus the probability of rolling on one time a 5 and a 6 simultaneously. The probability of rolling a 5 is 1/6 because you got one way to get a 5 out of 6 total possible outcomes. Plus probability of rolling a 6 is also 1 out of 6 because you have one way to get a 6 out of 6 possible outcomes. But the probability of rolling a 5 and a 6 in one roll, remember this is rolling a single die, rolling it one time. You cannot do that. Your die cannot land on 5 and 6 simultaneously. If you roll the die twice, then you can get a 5 and then a 6, but that's not what we're saying here in this problem because it said roll a single die. So you end up with 2 6 or 1/3, which is exactly what we had gotten when we just reasoned through it. Now down here, probability of an odd number or a number greater than 4. According to the formula, that's probability of odd plus probability of something greater than 4 minus the probability of odd and greater than 4. Okay, so probability of rolling an odd. You can roll a 1, a 3, or a 5. So that's a 3/6 probability. 3 out of 6 rolls should land on an odd. Plus probability of greater than 4. Remember, greater than doesn't include the 4, it's everything bigger. So that's a 5 or a 6. So that's 2 possible outcomes out of 6 total. 2 desired outcomes out of 6 total possible. But then when we do this, notice that we're getting 5 6 so far, but our answer had been 4 6. But remember, the 5 got counted twice here. It got counted under the probability of rolling an odd. It also got counted under the probability of rolling a greater than 4. So when you add 3 plus 2, when you add 3 plus 2, you get 5. But we don't want to count this same outcome twice. So the probability of rolling a number that's odd and greater than 4 is 1/6. So we have to subtract that out so that we avoid counting it twice. And then we see the correct answer. Okay, so sometimes the and part comes out 0 when these two things cannot occur simultaneously. Other times the and part does come out with some fraction, some probability, because those two can occur simultaneously. And you have to figure out the probability of that happening. And when that happens, you're subtracting out where you had counted double, when you had counted that joint outcome there double. So you have to subtract it one time out to make it correct. All right. So the stuff of sometimes the probability of A and B coming out 0, other times not, that has to do with whether two events are mutually exclusive or not. If two events cannot occur simultaneously, then the events are mutually exclusive. That was the example of you cannot roll the die and have it land on both 5 and 6 simultaneously. So the probability of A and B ends up being 0. So for mutually exclusive events, the OR formula basically gets condensed down to P of A or B equals P of A plus P of B. So in our previous slide here, let me change my color for a second. the probability of rolling a 5 or a 6, these in this case, we're dealing with mutually exclusive events. Oh, excuse me, my other computer just went to sleep. Down here, though, the odd number or greater than 4, these two are not mutually exclusive. And you can see that in the formula. So mutually exclusive, you end up with this 0 here. Not mutually exclusive, this was not 0. So that's the distinction. All right, let's do another example. Let me put my pointer color back to black here. All right, let's say we select one card from a standard deck. Standard 52 card deck. Okay, first let's figure out what is the probability of that card being a 10 or a 4. Okay, so we need to do the probability of a 10 plus the probability of a 4 minus the probability of 10 and 4 simultaneously. The probability of a 10. You have your 10 of hearts, 10 of diamonds, 10 of clubs, 10 of spades. So you got, what, 4 out of 52. Plus probability of a 4, 4 of clubs, 4 of hearts, 4 of diamonds, 4 of spades, 4 out of 52. When you draw that card, though, what's the probability of that card simultaneously being a 10 and a 4? Well, that's not possible, because each card has either its own number, or it's a jack or a queen or a king. You don't have 10 and 4 coexisting on the same card. So that can't happen. So that probability is 0. So we're dealing with mutually exclusive events here. The event of getting a 10, the event of getting a 4. All right, so 450 over 52 plus 4 over 52 is 8 over 52. And then that reduces down to 2/13. So that's that probability. Okay, starting with the fresh deck, draw one card. What's the probability of getting a jack or a spade? Okay, so in that case, probability of jack plus probability of spade minus probability of jack and spade. All right, so drawing the card, probability of a jack. You have a jack for each suit. So you have a jack of clubs, jack of spades, jack of diamonds, jack of hearts. So you have 4 out of 52. Probability of a spade, well, that's one whole suit. That's 1/4 of the card deck. So that's what, 13 out of 52 cards. 13 cards per suit. Minus, what's the probability of getting a jack and spade? Well, there is a jack of spades. So that's 1 out of 52. That jack of spades got double counted here. Got counted as one of the jacks, also got counted as one of the spades. So you have to subtract 1 out to make this accurate. 4 plus 13 is 17, minus 1 is 16 over 52. And then that reduces down to 4/13 divided by 4. So these are not mutually exclusive events. Jack and spade can coexist in one card. Okay, so there you have it. That's the situation for your OR problems. Your OR problems are not going to get any more complicated than that. Sorry, that noise is me just lying back into my other computer. So, not going to get any more complicated than that. You're not going to have to deal with OR problems with a bunch of different draws or rolls or whatever. They do exist, but you're just not going to get to that level. But what you are going to do, you are going to face AND problems where you are dealing with more than drawing one card or more than rolling one die. You've had the AND already in the OR formula, and that was still just, drawing one card, rolling one die, one thing. But now, let's look at what to do if you have to draw two cards or roll two die or, have more than one kid, that kind of thing. How can we find probabilities in those situations? Well, when you have multiple probabilities and you see the word AND, you're going to multiply. That's pretty common in mathematics, and you end up multiplying. Also, the word of, you end up multiplying. Happens quite a bit. One of those clue words. Okay, so let's go ahead and tackle a situation where you're going to have the AND problem. All right, in this situation, you have colored envelopes. I've already drawn the colored envelopes there on the top of the slide. You have 3 red, 2 blue, 1 green, and 1 yellow. Okay, and you're going to pick an envelope. Okay, you're going to select 2 envelopes at random. This is going to be with replacement. Very important. With replacement versus without replacement is very different. I'll specify why in just a second. And we want to figure out the probability that both are red. So that's the same thing as saying, what's the probability that the first one's red and the second one's red? Because we're picking 2 envelopes. Now in these problems, if it says select 2, you're selecting the first one, then the second one. If it says roll 2 die, you're rolling the first one, then the second one. Flip 2 coins, flip the first one, flip the second one. It's one thing before the other. It's not simultaneous. All right, so it's an AND question. There's more than one. So the formula says take those probabilities and multiply them together. Okay, so we got to take probability of drawing a red on the first pick. First one's probability of red on the first selection. Well, there's 3 red envelopes out of 3, 4, 5, 6, 7 envelopes. So the probability is 3/7. Now when you go to pick your second envelope, remember this is with replacement. So with replacement means you picked a red on the first pick, you got what you wanted on the first pick, you got red, then you put it back, you replaced it. Then you go ahead and draw the second envelope. You see what you got with that first one put back in there. So you again have a probability of getting a red as 3/7. 3 times 3 is 9, 7 times 7 is 49. That does not reduce. So there you go. So that's with replacement. Okay, now let's say they ask for you to find, still with replacement, the probability first is blue, then the second one is yellow. So that's probability of blue and yellow. So probability of blue times the probability of yellow. So probability of blue is 2/7. There's 2 blue envelopes possible out of 7. And what we're going to assume is that you grab that envelope and you grab a blue and you go, oh cool, I got what I wanted. And then you say with replacement, put it back. And then on the next draw, probability of getting yellow is 1/7. There's still 7 envelopes because you put the blue one back. You replaced it. 2/7 times 1/7 is 2/49. So that's and problems with replacement. All right, same scenario with envelopes. This time, let's select 3 at random. And this time it's without replacement. Okay. Probability, they are all red. So first selection's red, and second selection is red, and third selection is red. Okay, without replacement. First draw, there's 3 reds out of 7 envelopes. What we're going to assume is that you picked a red, and without replacement means you keep it, like you put it with your little pile or whatever, and when you go to draw the next envelope, the stash is now missing that red envelope because it was without replacement. So on the next draw, there's 2 red envelopes left out of 6 envelopes, out of 6 remaining envelopes. Then you assume, oh, on that second draw I got my red and I kept it. So on the third draw, there's 1 red envelope out of 5 possible envelopes. So you multiply all that together, you get 6/210, which does reduce to 1/35. 6 goes into 6 and 210. So without replacement, numbers change. It all depends on what your first probability was. You know, did you keep that? What was happening? Okay, now next one, probability that you first get red, then get blue on the second envelope, then on the third envelope get blue. Okay, so that's probability of red times probability of blue times probability of blue. Okay, so first draw probability of red is 3/7. 3 reds out of 7 envelopes. Now it's without replacement, so we assume you picked a red and kept it, picked 1 red and kept it. Next time around, probability of blue, there's 2 blues, but only 6 total envelopes because you had drawn a red the first time and kept it. Then on the third draw, there's only 1 blue left because you grabbed a blue on the second draw and kept it out of 5 remaining envelopes. 3 times 2 times 1 is 6. 7 times 6 times 5, 210. So you end up getting the same answer as the previous problem, but for different reasons. So there you go. Okay, so pay attention to whether it says with replacement or without replacement. Here we go. Independent events. The occurrence of one event in no way affects the probability of the occurrence of the other event. Drawing 2 items with replacement. So you pick envelopes with replacement. Picking the first envelope as red in no way affects what happens in the second envelope's probability because the red one gets put back in the pile. And it's as if you never took one to begin with. Whereas without replacement is dependent events. The occurrence of one event does affect the probability of the other event. So like without replacement, trying to draw red and then blue, the probability of drawing the blue was altered by the fact that you had to draw red on the first draw. So it's independent versus dependent. So going back, this was without replacement. So these were dependent events. Up here, the probability of all red and red and red is dependent events, because probability of getting a red on that second envelope was affected by the fact that you had drawn a red on the first envelope. Probability of getting a red on the third envelope was affected. That probability, the numbers depended on what happened in these first two draws. The fact that you have two reds now. Same thing down here with red, blue, and blue. Whereas with replacement, those are independent events. Because like here, drawing both reds, drawing a red on the second one, the probability was independent of what happened in the first one. First one didn't really matter because the red got put back in, and on the second draw, you're none the wiser. Probability doesn't get affected. Same thing here with doing the blue then yellow, as long as it's with replacement. So that's independent versus dependent. And as a summary, as I said earlier, your OR problems, you're typically going to see the word OR, and you're typically going to be just selecting one item. The OR problems, you can use that formula, or you can use common sense if the numbers are small enough. That formula has an AND in it, which in that case you're looking at AND being simultaneous. Like, can both this and that occur simultaneously? Now the problems that, the AND problems though, the ones we were just doing, usually involve selecting more than one item. You might not see the word AND in there. Like, you might just say, find the probability of drawing all three reds. Don't see the word AND there, but you can reword it and think, okay, probability of first red, and then a second red, and then a third red. You can reword it with the AND in there mentally. And you're going to assume that the first desired item is selected and that the probability is determined before the second item is chosen and that probability computed, and so on. And then the third, you're going to assume that you actually do select on each draw what's desired before, and then compute that probability before moving on to the next draw. So to compute that probability. All right, so that's your OR and AND problem. So now you've got some tools. If the tree diagram is going to be too much, now you can think about these formulas and how to find your probabilities with these instead of trying to draw out the tree diagram, draw out the sample space, because sometimes those sample spaces are humongous. And it's not really worth trying to sit there and draw that out and count everything. So instead, think about, well, how can I apply my formulas I've learned? All right. Well, I hope you have fun with this, and tune in again soon because we're going to be talking about conditional probability in the near future.